Okay, one of the first things we learn when we start electrostatics is we learn the field patterns for point charges, and that gives us Coulomb's law. So here I've written down the point charge field strength. I've taken out the direction, and that is equal to the Boltzmann's constant K. Remember, this is 9 times 10 to the 9th Newton meter squared, Coulomb squared, times the charge of the point charge divided by the distance squared that you are away from the point charge. So this gives you, if you have some point charge Q, this gives you the field strength at some location R, right? So you can pick 0.1, 0.2, 0.3, and as long as you know the distance away you are from the point charge, you can figure out what the field strength is at that location. And for direction, we use away from positive charges towards negative charges, okay? So this is a wonderful thing. I'm happy that, like all students, you appreciate Coulomb's law. Similarly, you appreciate that if we integrate this thing from r equals infinity to some r, if we integrate this Coulomb's field, dr, we get a very similar looking potential function. And because we choose the v equals 0 at infinity, this gives us a function for potential of a point charge, and it looks, like this. Okay, so these are our friends. We do appreciate them, but you need to be very careful because these expressions for field strength and potential only work sometimes, not all the time. When do they work? If you have point charges. Okay, if it says they're point charges, you can use it. Or if you have spherical shaped things and you have spherical symmetry of the charge inside. So you need an object that is spherical and you need a charge distribution that is spherical. It doesn't have to be uniform, but it has to be spherical charge distribution, okay? Spherical. Maybe what I'm saying is redundant. Some people would probably say that, but that's okay. You have to know it's a sphere and it has a spherical charge distribution, okay? If you don't have these two things, you may not use Coulomb's law. So why am I telling you this? They're often going to be, I don't know about often, but a common type of problem we see in the E&M test, the AP Physics C E&M test, is when you're given some sort of map, okay? Given some sort of map. This could be a field map. So it's showing you the electric field in space, or it could be a potential map. So it's giving you equipotentials. I'll try to draw one of each, okay? Equipotentials. So the equipotential maps are probably going to be more like cylindrical looking, kind of, okay? You'll probably have axes, so you might have an X and Y axis with some sort of origin. You'll have a 0, 0 here, and you'll have a scale with actual numbers, maybe, right? And also they'll probably tell you, if it's a potential, this is a potential map. They'll give you the spacing between lines. So the change in potential between lines is like, they'll say it's like, 20 volts. And they might tell you so this is 5 volts. So they'll give you the spacing between lines as 20 volts, and so this would be 25, whatever. Okay, if it's a field map, it's gonna have arrows on it. I don't know, I'm just making stuff up now. It's gonna have arrows on it. But the same sort of thing. Might have scales, axes on, so coordinate points, yeah. Bottom line is, these are not point charges. You may not use Coulomb's law for these. It just doesn't work, okay? What is okay is, like, if you remember from electric fields, the electric field lines leave positive charges point towards negative charges, that's fine. So you can imagine that somewhere off in the distance, there's like some more positive stuff, or over here, you might have more negative stuff. Fine, you can think like that if it helps you decide how another charge placed in that area is going to move, but it's not a point charge. Okay, so the common sorts of questions you will get asked here are to talk about, let me make a copy of this. That's cool. Okay. Okay, so what kind of questions can you expect if you see a map like this? You can expect questions like, where is the electric field the smallest? Strongest or weakest? I'm going to do a little extra work. Where is the electric field the strongest or the weakest? And usually for this, they're going to give you a choice of points. Okay, so they're going to give you some labeled points. Maybe here too, they're going to give you some labeled points like that. Oh, and they're not vectors. I don't know why I put a vector head on that one. Okay. They're going to say, where is the electric field strongest or the weakest? They're going to say, where is the potential the greatest or the smallest? Whatever. Or they could be high, low, whatever. They might use different words. They could ask you to draw either an electric field line or an equipotential line, depending on which map you have. Whichever one they gave you, you're going to have to draw the other one. They could ask you to estimate field strength at a given location. Or they could ask you for some sort of like conservation of energy kind of question, like find the speed of something if it's released in one place and ends up in another place. Or describe the motion of something. Yeah, describe the motion of something. So these are the kinds of questions they're going to ask you. The ones I want to talk about here specifically are, well, I guess maybe all of them. Okay. So that means I need another slide. Okay, so let's start by talking about the equipotential maps. I'm going to focus on this. If you're given an equipotential map, how would you answer these questions? Okay, so the equipotential map shows you the potential values, or at least some of them, and it gives you an idea of line spacing. So we're going to answer this one first. The map shows you the potential values. So where is the potential the greatest and the smallest? Looking at this map, I have two lines. I have a -5, I have a -25. If the line spacing is 20, I know this is going to be -45 volts, and this is going to be 15 volts, etc., positive. So I'm just going to find of these points, A, B, and C. A is in the area with the highest potential. C is in the area with the lowest potential. Okay, so you're going to read that right off the map. The second question you might be asked is, where is the electric field strongest or weakest? Okay, so here you want to look at the line spacing. So in this case, my equipotential lines are closest together near A, so I would say that the electric field strength is strongest near A, because the equipotential lines are closest together. And we'll talk about how to derive the value in a second. B would be the weakest field strength because around B the lines are the furthest apart, and C is somewhere in the middle. Okay, question 3. Well, let's go down here to estimate the electric field strength at a location. So to estimate the electric field strength at a location, we're going to start with this idea that the electric field in a particular direction is negative the derivative of the potential function along that axis. But we don't have a function. We don't have functions on the map. This is not a point charge. Do not use a point charge function. Coulomb's law. What you should be doing is saying, okay, we're going to make an approximation. So the approximate field strength value at A is going to be approximately equal to the change in potential across that area. And if we're just talking about strength, we don't even care about signs, divided by the change in position. So I know from the map it says it's 20 volts between lines. I have one line, another line, and I have to remember that this you get from reading the scale. So I would come down here and I would read the scale on my axis to get delta X. And I would plug in whatever number that was in meters, and I would take the fraction, and that would give me the field strength. You can check for yourself that volts per meter, a volt is a joule per coulomb, and divided by meter. Joules are Newton meters, that's a compound unit. So a volt per meter is the same thing as a Newton per coulomb. So this is a legit field unit. I can't emphasize enough, do not use the point charge function. You do not know what is going on with the charges here. Now, you may be asked, like, to write down any assumptions you make. You're going to say you assume the field is relatively constant in that region. That's how we get away with saying we can take the average field strength and it's close to the exact field strength. Okay. Conservation of energy questions. Well, let's talk about describing the motion because that's harder. Okay, describing the motion. So the first thing you need to know is that the electric field direction is the electric field is what's going to cause the force. So the force on the object is equal to its charge times the electric field direction. The acceleration of the object is equal to the force divided by the mass from Newton's second law. This is Newton's second law. Okay, so to describe the motion, you have to know which way the field points. And the field points towards low potential. Okay, so if we start at A is at a region of high potential. As we go towards B, C, that's lower potential. So the field around here is going to be towards the lower potential. That's because, like, the field points in the direction that is downhill. And that's true whether we're talking about, like, mountains or, like, charge fields, electric fields. Okay, fields point downhill. Downhill in our English language means towards lower potential. These things are kind of the same. That's how we define downhill. Just like we define down as the direction that the field points, the gravitational field. Okay. So the field direction is towards the lower potential. And then, so if you have a proton, protons follow the field. They roll downhill. They get faster as they move downhill. They will accelerate more if the field is stronger, meaning if the lines are closer together. So for something released at A, it's going to accelerate quickly in the positive x direction, but then its acceleration is going to decrease. So it's going to get faster quickly in the beginning, and then as it moves towards B, it's going to get faster more slowly. And it's going to continue getting faster as long as there is a field pointing in the positive x direction. Okay. Electrons go the other way. So electrons roll uphill. How can we see that? Rolling meaning getting faster. They get faster uphill, so they get faster in the other direction from the electric field. That's because the force is QE and electrons are negative, so that's going to flip the direction so that the force is opposite the field. Otherwise, you still have to talk about the same sorts of things. So an electron release near A would accelerate towards the left, and because those spacings are about the same, it's going to accelerate at a constant rate, just get faster and faster till it leaves the field area. Okay, conservation of energy. So we're going to write a standard sort of thing, UI plus KI equals UF plus KF. If we have to find a velocity and we know the starting and ending locations. But you have to remember, again, that these potentials, you're going to write them as QV. You don't have a function for V. You're just going to read it off the map, or they're going to have to give it to you. These are not point charge potentials. Just read it off the map. Okay, and you will get points for explicitly writing this as QV. You will not get points if you just leave it as U, apparently. So make sure you know that the electric potential is the product of the charge and the potential value at that location. Finally, drawing electric field lines or we're not drawing equipotentials because we already have them. These are perpendicular to the field. So starting by A, I'm just going to try to draw these so that I'm always perpendicular, and I need to make the electric field point towards lower potential. So if I go this way, perpendicular, and the field points towards lower potential. Here's another one. You really want to try to make sure as best you can that these are perpendicular. If you can't, put arrows on them. This one's going to do this. I'm having trouble getting over to that side, okay? Perpendicular. I hope that helped. Let's try the next version. How is the electric field map just different? So where is the electric field the strongest or the weakest? The electric field is the strongest or the weakest. Strongest where the electric field lines are closest together. Weakest where they're furthest apart. This is not so different from equipotential. So strongest maybe at, it looks like, so if I had to rank these, A and B have similar strengths, and those are both stronger than C because the line is like way further apart at C than it is at either B or A. Okay. Where is the potential the greatest or the smallest? So for this question, you have to know that the field lines point downhill. Remember that downhill in English is the same thing as lower potential. So because the field lines point downhill, the potential at C is the lowest. The potential at A is the highest. We don't know the absolute values of these, but we can say that the potential at A is higher than the potential at C because it is the furthest uphill. C is the furthest downhill. C is the lowest potential because it's the furthest down the field line. Let's see, draw, and so here we would be drawing the equipotential. It's the same idea. Equipotentials are perpendicular to field lines. If they give us some point we have to pass through, I'm going to try to draw this so that I'm coming in perpendicular to these field lines. Do your best to make them look perpendicular. So here, kind of like that. and definitely put the perpendicular sign on them, but if they look really not perpendicular, you're not going to get credit. Estimating the electric field at a particular location. So for this, again, you're using the idea that the potential difference, divided by the distance is approximately equal to the strength of the electric field in that direction. So here they'd have to give you the potential difference. So like maybe they say the potential difference around B is like, I don't know, around B. But then you're also going to have to measure the change in position. You're going to need to do that on the scale. So you have to read this change, this distance from the scale, and then you're going to estimate. And again, when you're doing this estimate, because you're not taking a derivative of a function, because you don't have a function, this is assuming that the field strength is approximately uniform in that region. It is approximation, and you're assuming that the field strength is constant enough in that region that the approximation is half decent. So describing the motion and conservation of energy are the same sorts of things. Remember that electrons roll uphill. They get faster uphill. So if you drop an electron at rest in here, it's going to move towards A. It's not going to move towards C. A proton would go from A towards C. And if the field strength gets weaker, if the lines get further apart, then the acceleration of that object is going to be smaller. You're still dealing with the same sorts of equations. So the force is equal to QE, and therefore the acceleration is equal to QE over m. You can still say that. Don't forget directions. And finally, conservation of energy. It's the same sort of thing as with the field maps. You absolutely need to be saying that the potential energy is the product of Q and potential. You don't know a function. This is not a point charge. So you're going to put it in as a generic potential energy equals QV and do it that way. All right. I hope this helps. It's kind of messy, so hopefully you took notes and you can write it down in a way that makes sense to you. These are not uncommon questions to show up.